right? So so now we come to the point of now we have a set of samples, including the samples for the tail. How do we effectively calculate the crash probability without actually having to go through the simulation for many millions of times? What's the best way to do that?
Only sample a subset of the distribution of each of the distributions.
So here is a suggestion: only sample a subset of the distributions. How do we do that? Like what kind of subset are you thinking of sampling?
You have to figure out, so like for any t, what is the delta v cutoff that sort of guarantees that you're safe, and then for any delta v, figure out what the t cutoff that guarantees that you're safe is, and then only basically ignore the area where you know it's safe. I mean, you have to calculate that area to find the final probability, but then only sample. If you sort of divide the bivariate distribution into 4 quadrants, only sample the 3 quadrants where you're not guaranteed to be safe.
Right. Okay. So we have a very good suggestion here. Here we have a 2-dimensional probability space, right? So let's draw our omega. The probability space is the space of delta v and t. So we know delta t can go all the way to 0. It's very unlikely. Delta v is very small, but the probability is nevertheless not going to be 0. And t also can go all the way to infinity, although the probability is small, it's not 0. So we have the space is over here, right? So that's the random space we are interested in. So the suggestion is maybe there is a part of this random space where even without performing the simulation, we would know that it wouldn't crash. So, for example, if you can figure out such a region, we can basically carve out the region, right? So, this region is probably for a large delta t and a large delta v and small t. So, for example, if you can carve out this region and say this region is safe, and the remaining regions, I'm gonna. So what I'm gonna be doing is for every sample, I'm gonna look for if I'm in this region or not. If I'm not in this region, I'm gonna perform a simulation. If I'm in this region, I'm going to count it as 0 probability, right? So that's a very smart method of reducing the number of simulations you have to do. What if I have a scenario where, let's say, the simulation might be complex enough that carving out this region is very difficult? So for example, if the firing the retro rocket and if the procedure actually involves solving a differential equation, right? So it's a lot harder to carve out this region specifically. Or let's imagine if I have a lot more than 2 random variables. If I have 10 random variables, then it's a lot harder to carve out a space in the 10-dimensional space, right? So what should I do in that scenario? Anyways, I can reduce the number of samples.
You just cut off, like, just sample the tail. You can find like what percentage of that whole area is the tail, and just sample the tail.
So the suggestion is, can I just sample the tail? I mean, both of these suggestions are good suggestions in the sense that I want to focus on the tail, which are more likely to give me a failure, right? So one approach is to try to ignore the region where it's impossible to give me the failure, but oftentimes it's not really possible to say with 100% probability that this is the region that will never give me a failure. But it's actually not that difficult to say, okay, for for larger delta V and smaller t, it's much less likely to fail, right? That's much easier to say. And also, you are saying focusing on the tails, which means for example, for small delta V, large t, it's actually much more likely to fail. So put more emphasis on the region that is more likely to fail, and less emphasis on the region that is less likely to fail. Is a very good approach. But actually, specifically, how do we do that?